projects. In this video, we are going to explain about the project title, Detection of Real-Time Malicious Intrusions and Attacks in IoT-Empowered Cybersecurity Infrastructures. Introduction. The project recognizes the urgent necessity to enhance cybersecurity with IoT-empowered systems, particularly focusing on industrial control systems (ICS). This highlights the criticality of securing these infrastructures due to the extensive integration of IoT technologies. The widespread adoption of IoT technologies has significantly raised concerns regarding potential malicious activities and cyber attacks. This necessitates the implementation of advanced intrusion detection system to effectively protect and secure IoT-powered infrastructures. The rapid growth of IoT devices, particularly in the industrial IoT sector, has brought forth distinct security challenges. Current IDS face difficulties in achieving optimal detection rates and often produce false positives, highlighting the urgency for an enhanced and more efficient approach to intrusion detection. To address the mentioned challenges, the project plans to utilize an ensemble method. This approach aims to enhance detection accuracy while reducing false positives, demonstrating the project's commitment to adopting innovative strategies for more effective intrusion detection in IoT-based cybersecurity infrastructures. Objective. The main objective is to enhance the security of IoT infrastructures by effectively detecting and mitigating real-time cyber threats and intrusions. This focus ensures that the systems remain secure and operate with integrity. The proposed framework aims to overcome the limitations of traditional intrusion detection systems that often suffer from poor accuracy, ineffective detection, and a high rate of false positives. This emphasizes the need for an improved and more precise approach to intrusion detection. The project aims to leverage advanced deep learning techniques such as recurrent neural network (RNN), convolutional neural network (CNN), and deep neural network (DNN). These techniques aim to create a highly accurate and reliable intrusion detection system tailored for IoT environments, capable of identifying a wide array of cyber threats with improved accuracy. Another objective is to ensure the confidentiality and integrity of sensitive information belonging to both users and the systems themselves throughout the training and the testing phases of the intrusion detection system. This underlines the commitment to maintaining data security and privacy at all stages of the project. Requirements. The requirements of the project are hardware requirements, in which we have operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements, in which we have Anaconda 3 and Visual Studio Community version. Flow of project. To implement this project, we have designed the following steps. The first step is importing the packages. In this step, essential Python libraries and packages are imported. These packages include tools that are fundamental for data manipulation, analysis, and visualization. For instance, Pandas used for data manipulation and analysis with its data frame structure. Matplotlib, a versatile plotting library for creating static, animated, and interactive visualization in Python. Seaborn, a statistical data visualization library based on Matplotlib that provides a high-level interface for drawing attractive and informative statistical graphs. Exploring the dataset. Here, the project dives into the datasets that are crucial for training and evaluating the intrusion detection system. Different datasets, KDD CUP99, NSL KDD, and UNSW NB15 are explored to understand their contents, features, and structure. This step helps in gaining insights into the data that is being worked with. Data processing. Data processing is a critical step where the raw data from the dataset is organized and prepared for analysis. This involves converting the data into a structured format like a Pandas data frame or a Keras data frame, which facilitates easier handling and manipulation of data. Additionally, irrelevant or redundant columns are removed, dropped to streamline the dataset for further analysis. Visualization using Seaborn and Matplotlib. Visualization is a powerful tool for understanding the characteristics of the data. Seaborn and Matplotlib are employed to create visual representations of the data such as plots, charts, and graphs. These visualizations offer insights into the distribution of data, correlations between features, and patterns that are vital for making informed decisions during the development of the intrusion detection system. Label encoding using label encoder. In this step, categorical data is converted into numerical format using label encoding. This is necessary because many machine learning algorithms require numerical input, not categorical. The label encoder assigns a unique numerical label to each category, allowing the machine learning model to process the data effectively during training and evaluation. Feature selection. Feature selection involves identifying the most relevant features from the dataset that contribute significantly to the model's performance. Various techniques can be used to accomplish this, such as select percentile using mutual information, which assesses the importance of features based on their relationship with the target variable. Splitting the data to train and test. The dataset is divided into two sets, a training set and a testing set. The training set is used to train the machine learning models, while the testing set is reserved for evaluating the performance. This ensures an unbiased assessment of the model's generalization capabilities. Building the model. Different deep learning architectures are employed to build the intrusion detection model. CNN, convolutional neural network, suitable for analyzing grid-like data such as images or time series data, and widely used in detecting patterns in network traffic for intrusion detection. RNN LSTM, recurrent neural network with long short-term memory, effective for handling sequential and time series data, making it suitable for modeling patterns in network traffic for intrusion detection. DNN with MLP, deep neural network with multi-layer perceptron, a classic neural network architecture suitable for general pattern recognition, including intrusion detection tasks. An ensemble method combines the predictions of multiple individual models to create a more robust and accurate final prediction. Techniques like bagging, boosting, or stacking may be used to achieve this. We have built front-end using Flask framework for user testing and with user authentication. Training the model. The selected models CNN, RNN, LSTM, DNN with MLP are trained on the pre-processed training data. During training, the models learn to identify patterns and features in the input data related to intrusion and normal activities. Flask framework with SQLite for sign-up and sign-in. A front-end is created using the Flask framework to provide a user-friendly interface for interacting with the intrusion detection system. Flask allows for the design and deployment of web applications, making it suitable for user testing and authentication. User gives input as feature values. Users input feature values representing network traffic data. This input is pre-processed to align with the model's input requirements, which include scaling, encoding, or any other necessary transformations. The given input is pre-processed for prediction. The pre-processed input is fed into the trained models for prediction. Each model predicts whether the input represents a malicious intrusion or not. Trained model is used for prediction. The pre-processed input is fed into the trained models CNN, RNN, LSTM, DNN with MLP for prediction. Each model predicts whether the input represents a malicious intrusion or not. Final outcome is displayed through front end. The predictions from the models are combined to generate a final prediction. The outcome, indicating the presence or absence of intrusion, is displayed to the user through the front end. Comparison graph. To implement this project, we have used KDD Cup 99 dataset. KDD Cup 99 is one of the earliest and most widely used dataset for intrusion detection research. This dataset contains a substantial amount of network traffic data that simulates a network environment, including both normal and various types of malicious attacks. KDD Cup 99 serves as a benchmark dataset for building and evaluating intrusion detection models for IoT-enabled cybersecurity systems. This is the accuracy comparison graph of KDD Cup 99 dataset. On the x-axis, we have the accuracy score, and on the y-axis, we have the algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances to the total number of instances. This is the precision comparison graph. On the x-axis, we have the precision score, and on the y-axis, we have the algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives to the total number of positive predictions. True positives plus false positives. This is the recall comparison graph of KDD Cup 99 dataset. On the x-axis, we have the recall score, and on the y-axis, we have the algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances. True positives plus false negatives. This is the FN comparison graph. On the x-axis, we have the FN score, and on the y-axis, we have the algorithm name. The FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. In this project, we have also used NSL KDD dataset. NSL KDD is an enhanced version of KDD Cup 99, providing a more refined and balanced dataset for training and evaluating intrusion detection models for IoT cybersecurity. This is the accuracy comparison graph of NSL KDD dataset. On the x-axis, we have the accuracy score, and on the y-axis, we have the algorithm name. This is the precision comparison graph. On the x-axis, we have the precision score, and on the y-axis, we have the algorithm name. This is the recall comparison graph of NSL KDD dataset. On the x-axis, we have the recall score, and on the y-axis, we have the algorithm name. This is the FN comparison graph. On the x-axis, we have the FN score, and on the y-axis, we have the algorithm name. In this project, we have also used UNSW-NB15 dataset. UNSW-NB15 offers a more up-to-date and relevant dataset for developing intrusion detection models in IoT-empowered cybersecurity infrastructures, allowing researchers to count for evolving attack methodologies and IoT-specific traffic characteristics. This is the accuracy comparison graph of UNSW-NB15 dataset. On the x-axis, we have the accuracy score, and on the y-axis, we have the algorithm name. This is the precision comparison graph. On the x-axis, we have the precision score, and on the y-axis, we have the algorithm name. This is the recall comparison graph of UNSW-NB15 dataset. On the x-axis, we have the recall score, and on the y-axis, we have the algorithm name. This is the FN comparison graph. On the x-axis, we have the FN score, and on the y-axis, we have the algorithm name. Execution. To execute this project, first we need to open the code folder, which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is IPYNB file. This is a Jupyter notebook file which contains a combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is model file which contains algorithm information which will be loaded into the project code during runtime. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. I am copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. Here I am typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, which is this localhost and port. Now copy this local link provided by the Flask framework. I am copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. This is the homepage of the project displayed in the browser. This is the front end built using Flask framework. Now click on sign up button to register. If we are a new user, we need to register first, but I have already registered, so click on sign in button. So here we need to enter the username and the password which we have created and then click on login. So we have logged in. So here we need to enter all these parameters first. Then we will predict the attack and its type. So I'm entering the parameters. So here I have entered all these parameters. Protocol type is 1. Protocol type represents the type of network protocol used. Example, TCP, UDP, ICMP. Service is 19. Service denotes the network service being accessed or utilized. SRC bytes is 9. SRC bytes indicates the number of source bytes in a network connection. DST bytes is -0.01242. It represents the number of destination bytes in a network connection. Logged in is -0.03888. Identifies whether a user is logged in, binary indicator. Count is -0.09653. Reflects the number of connections to the same host has the current connection in the past seconds. SRV count is -0.09062. SRV count denotes the number of connections to the same service has the current connection in the past seconds. SRV different host rate is -0.80228. It represents the rate of connections to different hosts for the same service. DST host count is -0.02309. It indicates the number of connections to the same host in the past seconds. DST host SRV count reflects the number of connections to the same service on the destination host is -0.72996. DST host same SRV rate is -0.35384. Denotes the rate of connections to the same service on the destination host. DST host different SRV rate is -0.2863. It represents the rate of connections to different services on the destination host. DST host same SRC port rate is 1. It indicates the rate of connections to the same port from the same source host. DST host SRV different host rate is 7.66. Denotes the rate of connections from the same service to different host on the destination host. So now click on predict. So we got the result, there is no attack detected and it's normal. Now we will enter another set of parameters. So I'm entering another set of parameters now. So here I have entered another set of parameters. Protocol type is 1, service is 45, SRC bytes is 9, DST is -0.012, logged in is -0.03, count is -0.09, SRV count is -0.09, SRV different host rate is -0.80, DST host count is -0.02, DST host SRV count is -0.72, DST host same SRV rate is -0.35, DST host different SRV rate is -0.28, DST host same SRC port rate is 1, DST host SRV different host rate is 7.66. Now click on predict. We got the result, attack is detected and it's DOS attack. So in this way, by entering all the parameters, we can predict the attack and its type. Now sign out. The conclusion of the project is, the project showcases the potential of leveraging deep learning methods like RNN, CNN and DNN to significantly improve cybersecurity by enabling early detection of cyber attacks and identification of malware. The selection of an ensemble model for prediction based on its exceptional accuracy and F-score compared to individual models underscores its effectiveness in enhancing the overall accuracy and reliability of the intrusion detection system. Integrating the system with Flask enhances accessibility and user-friendliness, enabling practical and user-friendly deployment of the intrusion detection system, which is vital for users seeking to enhance online security. Additionally, the project lays the groundwork for future advancements by advocating for advanced deep learning integration and emphasizing the importance of robust intrusion detection system for real-time detection and classification of malicious activities.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.